Evolution tends to reward cognitive processing power. It seems logical to assume that the sharper a mind is, the easier a time that individual will have, adapting to complex social structures and thriving in group dynamics. This exact assumption formed the core of early differential psychology. In the 1920s, psychometricians championed what became known as the harmony hypothesis. Early intelligence tests were administered under the premise that superior intelligence was a universal advantage across all domains of life. Researchers tracked high-ability cohorts and mapped a strict linear correlation. They observed that as cognitive capacity increased, so did a person's psychological resilience and overall social adjustment. Modern educational and institutional systems were designed around these exact findings. The prevailing logic dictated that gifted individuals naturally possess the tools to navigate interpersonal challenges, requiring absolutely no specialized socio-emotional support. The idea that extreme intelligence guarantees social success became the bedrock of modern educational psychology. Yet, clinical data from recent decades reveals that this baseline misses a crucial threshold. To track lifelong adaptation accurately, researchers utilize quadratic and spline regressions. Long-term evaluations, such as the 1970 British cohort study, examine mental health outcomes across the entire spectrum of cognitive ability. This chart maps IQ against socio-emotional adaptation. The harmony hypothesis predicts a constant upward trajectory, yet actual cohort data paints a different picture. The protective correlation holds initially, but as cognitive capacity reaches extreme upper values, the trend flattens and abruptly reverses. At extreme values of intelligence, the protective correlation flattens and reverses, triggering unique socio-emotional difficulties. Past a specific threshold, higher intelligence stops acting as a social shield and starts functioning as a liability. Clinical psychologists evaluate this drop-off through the lens of person-environment fit theory, which examines the alignment between an individual's personal characteristics and the specific demands of their surroundings. The chronic isolation documented in highly intelligent populations is not a pathological defect. It is the direct structural consequence of a severe ecological mismatch. The roots of this mismatch begin in early childhood. Gifted populations frequently exhibit asynchronous development, an uneven rate of cognitive, physical, and socio-emotional maturation. Here we see two bar charts representing developmental timelines. For the majority of the population, cognitive age and emotional age rise in tandem. In the profoundly gifted model, these variables decouple. Cognitive capacity accelerates rapidly, operating years ahead of the individual's baseline. This split occurs because cognitive capacity and emotional capacity operate as orthogonal intelligences. Psychometrically, the two metrics are independent of one another. Superior working memory and the ability to conduct abstract analytical processing provide immense computational power. They do not mathematically predict an individual's capacity for emotional self-regulation or social empathy. The result is a severe functional asymmetry. A person can quickly deconstruct complex systemic logic while simultaneously lacking the normative algorithms required to initiate casual small talk or build group trust. When forced into standardized social hierarchies, this internal developmental split guarantees interpersonal friction. The individual is placed in environments matched to their physical age, but their cognitive processing requires something entirely different. In the 1920s, researcher Leta Hollingworth identified the limits of this friction, defining what she termed socially optimal intelligence, a cognitive range falling roughly between 125 and 155 IQ. This Gaussian bell curve illustrates the distribution of IQ scores. Highlighting the normative center at 100, we map a shaded region extending 30 points in either direction. Hollingworth classified this as the zone of communicability. When the center of that zone shifts to an extreme score of 145, the bracket moves into the far right tail of the curve. This represents a mathematically exponential drop in available peers. This visualizes the 30-point communication rule. When the cognitive discrepancy between two individuals exceeds 2 standard deviations, mutual conceptual exchange breaks down entirely. The breakdown is linguistic in nature. The extreme high IQ band processes language through first principles conceptual construction, combined with the simultaneous tracking of multiple logical layers. The normative communication bandwidth operates differently. It relies heavily on linear, step-by-step processing and the use of received phrasms, culturally understood stock phrases, that allow for smooth social interaction. In conversation, the high IQ participant skips steps to state an endpoint, which observers perceive as pedantic or magically associative. Conversely, the highly intelligent individual often finds the normative reliance on stock phrases to be logically incoherent. Neither party is intentionally shutting the other out. The communication barrier is a mathematical certainty, dictated by standard deviations, leaving the gifted individual structurally isolated from the surrounding population. The internal reality of this isolation is explained through Kazimierz Dąbrowski's theory of positive disintegration, specifically his identification of overexcitabilities in high-ability populations. Overexcitabilities represent heightened, intense central nervous system responses to stimuli. They cause the individual to absorb environmental tension, complexity, and sensory data at overwhelming volumes. While the surrounding environment operates at a baseline frequency, the gifted nervous system is rapidly processing an excess of data, resulting in severe neurological friction. There is a steep evolutionary penalty for operating out of sync with the group. To mandate cohesion and ensure survival, the mammalian brain is hardwired to register chronic social isolation as physical pain within the anterior cingulate cortex. Looking at this schematic of the brain, we can trace how a chronic social mismatch acts as an environmental input signal. That signal directly triggers the HPA, the hypothalamic pituitary adrenal axis. That activation initiates a biological cascade. It elevates baseline cortisol levels and disrupts normal neuroplasticity. At the genomic level, this stress response drives the overexpression of NF-kappa B/ARL transcription factors, shifting the body into a chronic pro-inflammatory state. This cognitive gap exacts a measurable neurobiological cost, directly linking structural loneliness to accelerated physiological decline. The burden associated with profound intelligence is a failure of person-environment fit. It is not an inherent psychological flaw, nor a deficit of character. Yet, traditional institutions consistently prescribe the same remedy: socialization. They demand that the outliers suppress their cognitive intensity and alter their communication style to conform to normative group averages. This approach forces the individual into prolonged periods of cognitive masking. Suppressing natural processing speeds and conceptual curiosity drains mental resources, leading directly to deep psychological burnout. This grid represents standardized social structures. Attempting to force an outlier into a space not designed for their architecture doesn't integrate them. It only serves to fracture their identity. Clinical evidence points toward a much more effective intervention, termed social development. Unlike socialization, which focuses on conformity, social development involves the active cultivation of environments designed specifically for the outlier. It prioritizes spaces where conceptual exchange operates exactly at their required bandwidth. True psychological adaptation for extreme intelligence does not involve reducing cognitive intensity to match a standardized environment. It requires locating the rare, specialized networks where their zone of communicability perfectly aligns.